Alright, today I'm going to be going over the Chatelier's principle. Now, this principle is a fundamental idea that applies to dynamic equilibrium in chemistry. So, if you need help, watch this video. So, let's imagine this. Say we have A plus B yields C plus D. Okay? Now, the Chatelier's principle states that when a stress is added to either the products or the reactants, such as increasing the concentration of a product or reactant, adding temperature, adding pressure, decreasing pressure, all these stuff, the system will do its best to sort of counteract whatever stress was added. So, for example, one stress can be adding reactant. Say I add A, okay? I increase the concentration of A. What will happen? Well, whenever you increase the concentration or you add a reactant to a system, Le Chatelier's principle states that the reaction the system will shift to the right, which means that more forward reactions will be happening instead of reverse reactions temporarily, okay? This is due to the fact that we're adding more reactant, right? As we add more A, whatever substance A is, as we add more A, then now we have excess A. We have excess substance A that the system now uses in more forward reactions. Since we have more A, the system uses the A to conduct more forward reactions in order to sort of set the bar down. So we can envision it like this. Say we have a bar, right? If we increase the bar, Le Chatelier's principle wants to decrease the bar just to get it back to this perfect little equilibrium state. This little perfect equilibrium state, you know? So, when we add reactants, this can either be A or B. The system will shift to the side of the products or the right. Now, this is the same for B as it is also a reactant. Now, what if we decrease the reactants? Well, it's the same concept. We have the bar. Think about the bar. If we decrease A, Le Chatelier's principle wants to sort of reset the bar to back to its equilibrium state. So, if we remove A, what does the system want to do now? It wants to create more A. So what does this mean? Well, the forward reaction produces more C and D, but no, we want to produce more A. And the reverse reaction produces more A. So what will happen? If we decrease A, the system shifts to the left, to the reactant side. As we decrease reactants, the system shifts to the reactant side. You know, if the system's in a perfect equilibrium state and you decrease the concentration of a reactant, it wants to get back to equilibrium, so it's going to want to make more reactants to kind of reset it. In that case, does the forward or reverse reaction create more reactant? The reverse reaction creates more reactant. So in this case, it's going to shift to the left, favoring the reverse reaction, causing more of the lost reactant to be made up. Okay. Now, say we change a product. It's honestly the same exact thing. So say we increase the concentration of C, okay? What do you think will happen? If we increase the concentration of C, we create excess C, we add too much C. The system wants to sort of use up that excess that C and get the system back to equilibrium. So the system shifts to reactants left. You know, we added more C to the system, and the system's like, bro, we have too much of the C now. Like, what are we doing? We were in perfect equilibrium. You added more C, so I'm gonna use that C to create more reactants. I'm using that excess C, and by using that excess C, I'm causing more reverse reactions, favoring the reactants, creating more reactants. It's using up that excess product that you added to create more reactants to balance it out. Same concept. And honestly, when I write C is replaceable with D because they're both reactants, and A can be replaced with B. So if we decrease C, the system will shift to the products. Now that we've covered the basics, I've assigned a state of matter to each of these substances that we have in our reaction. So as you can see, we have B and C are gases, A is aqueous, and D is a solid. So what would happen if we were to increase the concentration of D? Nothing would happen because solids do not have a concentration. This applies to liquids as well. Liquids and solids don't have concentrations because we don't refer to them as amount per volume. They have a fixed amount per volume. They have a fixed density. You can't change the concentration of a solid or a liquid. So the Chatelier's principle does not apply to solids or liquids. Okay, now that we've gotten that out the way, we can see we have B and C. B and C are both in the gaseous state. Well, what does that mean? Well, gases and aqueous compounds, substances, they both have concentrations, okay? So, yes, the Chatelier's principle does apply to gases. But let's think about this. We can think of concentration when we're referring to gases. Concentration is the same as pressure. What is concentration? It's the amount in a certain volume. Pressure is the same thing for gases. So, when we refer to gases in Le Chatelier's principle, instead of saying we're increasing the concentration of this gas, we often say we're increasing the pressure of this gas. The partial pressure of B, the partial pressure of C. So let's think about that. What would happen if we increased the partial pressure, the concentration, the pressure of B? Well, as we stated before, when you increase a reactant, you have excess reactant, which causes the system to shift to the right, favoring the products, favoring the forward reaction. So all that excess reactant can be used to make more product. So we can go back to a constant concentration. As we know, dynamic equilibrium has constant concentrations. So we're assuming, yes, it wants to shift to the products to use up all that excess B that we added. But this is when it gets a little tricky. Our goal is to decrease the total pressure of the system because, we increase the concentration of B, increase the pressure. We're expecting a decrease of pressure to happen after we shift to the products, because that's Le Chatelier's principle. It's going to shift to the products. We increase reactant, it's going to shift to the products. However, since our products, also before I say this, pressure only applies to gas molecules, so changing the pressure will not affect A at all. So I'll just cross A out. Since that we have 2 moles of C, when we increase the pressure of B and we shift the system to the products, we shift to the right, we favor the products, we end up increasing the pressure significantly because now we're favoring the reaction that yields 2 moles of a gas, whatever gas. So now by causing more forward reactions, we're making a bunch of C. We're making a bunch of C. And that's increasing the pressure like crazy. The pressure is increasing like crazy. And since the pressure is increasing like crazy, what does Le Chatelier's principle do? What does the system do? Now the system will shift back to reactants. By shifting to the products initially, we end up creating so many moles of whatever gas C is, and that just causes excess pressure. And what does the system want to do? It wants to make up for that excess pressure by favoring the side of the reaction that yields less gas molecules. In this case, it would be B. So when we increase B, the partial pressure of B, we're not actually increasing the products anymore because the products have more moles of gas. By increasing the products skyrocket, and this causes the reaction to go back to the left and, balance out the little system, get back to equilibrium. So this comes to this idea. Many times when we're referring to like pressure, Le Chatelier's principle, we often just say the pressure of the system as a whole. It's because the idea that comes from this is the exact same as this, but it's less steps. Okay? When we increase the pressure as a whole, the system will shift to side less gas moles / molecules, less moles of gas. We see this in our previous example. We increased B, or we just increase the pressure in general, because as we increase B, we're also increasing the pressure of C. So we're increasing the pressure of the total system. And it ended up shifting back to the reactants, the side with less gas. If we were to increase C, for example, we increase C, the reaction would shift to the left, because that's what happens when you increase a product, the system favors the reactants to make up for that excess product. So if we increase C, we are increasing B. Actually, we are also increasing B, and that makes up for the excess pressure. Rather than before, when we increased B, we were yielding so many moles of C when it was just too much pressure. So by doing this, the pressure is evened out, the pressure is balanced out. So the same thing applies. It will shift to the side with less moles of gas. Now what if we decrease the pressure? It's the opposite. It will shift to the side more gas. Think of it like this. As we know, volume and pressure are inverse. If we were to decrease the pressure, volume increases. Volume increases. Now, what does the system want to do for this excess volume that we have? Will it rather favor the reaction that only makes 1 gas mole? 1 mole of gas? Or favor the reaction that makes 2 moles of gas? Well, which one will fill up the excess volume quicker? Obviously, the one with 2 moles of gas. It will just fill up the excess volume quicker, and it will allow the system to reach its equilibrium in a more efficient method than favoring the reaction with only 1 mole of gas. So as we decrease the pressure, we are also increasing the volume. And all that excess volume, the system wants that excess volume to be filled up with more gas. So it's going to favor the reaction that yields more gas. So as we decrease pressure, the reaction will shift to the side with more gas to create even more gas that we're losing because of the excess volume, the decrease in pressure. Now, what happens if temperature is increased or decreased? Well, first of all, we want to identify whether the reaction is exothermic or endothermic. This reaction here we have is exothermic because it yields energy, it yields heat. So when we have an exothermic reaction, we can think of heat as a product. We can see it's on the product side. We can think of it as a product. So now, what would happen if we were to increase the temperature? If the heat is a product, if we think back to the fundamentals of Le Chatelier's principle, when you increase product, the system shifts the side of the reactants. It wants to sort of make up for that excess product, so it uses up that product to conduct more reactions that favor the reactants. So the system will shift to reactants. And vice versa is for decreased temperature. If we were to decrease the temperature, the system wants to make up for that loss of temperature, so it will shift. Well, that was typo. It will shift to the products in order to make up for that excess heat that was lost. Now, what if the reaction was endothermic, like we have right here? Well, we can think of heat in this case as a reactant. So, think back to our basic knowledge of Le Chatelier's principle. When we increase a reactant, in this case the temperature, what will happen? The system will shift to products. We have excess reactant. What will the system do with that excess reactant? It will conduct more reactions with that reactant to, lower it back down, and that ends up in more reactions towards the products happening, more product being produced. And if we decrease the temperature, if we decrease a reactant, it will shift to the reactants. So, although there are three different changes, the main three changes are pressure, temperature, and just concentration, and they, at first glance, they all seem very different from each other. The same fundamental principle and idea is behind it all. You increase whatever, anything. If you increase the bar, it wants to get back to its equilibrium state, so it will just decrease. It will decrease the bar, right? What can it do to decrease the bar? What can it do to to make up for the excess stuff added, the excess heat added, the excess pressure added, the excess concentration added? It will try to counteract that and do the opposite. We have excess heat, it's going to use that heat. We have excess concentration, it's going to use that extra stuff added. And in that case, we can say, oh, it's using it, it's going to shift to the other side, referring to it's using that stuff that we added, and it's causing more of the reaction, which yields the other stuff to increase. But yeah, I hope this video was helpful. I have a test tomorrow, so I'm trying to study for it. And I thought, what would be a better way for me to study than to teach, I guess. And why not make a video and teach whoever needs help, I guess. So it's my first video. It wasn't the best. They will get better in the future. So yeah, I'm still getting comfortable on screen, whatever. Alright, subscribe. Thank you. Peace.